Hello everyone, this is Prof. Lee. Let's solve this problem. In this problem, we have a translational spring mass system with combined springs. So we have a parallel and series configurations. Our system is 1 degree of freedom system since we have one mass. Therefore, we only need one coordinate to express our motion of the mass. Let's solve this problem. In this problem, we have to find first one equivalent spring constant, K over EQ, which represents the overall stiffness of the system. And also, we have to provide a free body diagram first when the mass is in equilibrium. And we also have to provide the free body diagram when our mass is in motion with a small deflection. We have to provide the kinetic diagram for the motion. From this, we're going to derive our equation of motion using the equivalent spring constant. And once we have equilibrium motion, we can also determine natural frequency of the system. Let's take care of the given information first. Mass is given. Spring stiffness for each spring is also given. We have 5 springs. From this, we have to find one single equivalent spring constant, K over EQ. Also, we have to provide free body diagram for equilibrium and for motion with the kinetic diagram. And from this, we're going to derive our equation of motion. Lastly, we have to provide natural frequency for the system. Let's start our solution. First, to find the equivalent spring constant K over EQ, let's recall how to find the equivalent spring constant for parallel and series configuration. Parallel configuration, we assume when a load is applied to spring, the springs undergo a same displacement. With this, we can actually derive equivalent spring constant for parallel configuration can be found by K over 1 plus K over 2. If we assume we have n springs connections, we're going to add all the spring constants for the parallel configuration to find one single equivalent spring constant. Then what about series configuration? For the series, we assume that when a load is applied, the springs are subjected to the same force. With this, we can come up with the equivalent spring constant can be found by 1 over K over 1. Again, we do have n spring connections plus 1 over K over 2 plus up to 1 over K over n. And then finally, we take inverse value of them to find one single equivalent spring stiffness for the series configuration. With this recall, let's do step by step to deal with these combined springs connections. Let's take care of the upper portion of spring connections here. If we see the upper portion parallel connections, and therefore we can add them together to find one single spring constant from these parallel combinations. Therefore, the upper portion of the spring constant can be expressed as K over 1 plus K over 2. Then let's move to the bottom portion here. The bottom portion we have parallel for the left, the right side spring, we also see the series combination. First of all, let's keep the left portion which has a spring constant K over 3. Then we're going to express these two springs K over 4 and K over 5 with the series combination as one spring constant. How to? We can express 1 over K over 4 plus 1 over K over 5. Don't forget, we have to take inverse value from them. So then let's move to the next step, the top portion of the spring combination, K over 1 plus K over 2. Then we're going to come up with one spring constant from this bottom portion of this parallel combination. How to? K over 3 plus this value from the right spring. Since they do have a parallel combination, K over 3 plus, then the right portion can be written as K over 4 times K over 5 divided by K over 4 plus K over 5 with this inverse relations. Lastly, we can express these two parallel combination as one equivalent spring stiffness because this top portion, this bottom portion, they're the parallel combination. So we can actually find one single spring constant K over EQ, add them together. And therefore, this one single equivalent spring constant can be found by the top portion K over 1 plus K over 2 because they are the parallel connection. We can also add the bottom portion of the spring stiffness. From this, we're going to move to the next problem. To derive our equation of motion using Newton's law of motion, we're going to provide a free body diagram starting from equilibrium. Let's draw our free body diagram FBD on the bar and when our mass is in equilibrium. Okay, so already I draw and outlined our body here. Then let's show all the forces acting on it, starting from the active force. From the mass, weight will act in the gravity direction. How much? mg much. And also, due to the mass, we do see the spring force will act upward direction. From the mass to our system is trying to move to the downward direction. The spring will act upward direction to restore the energy. Therefore, opposite direction, upward. How much? Spring stiffness, K equivalent, times static deflection, delta of ST. That's going to be our free body diagram. Once we have this free body diagram for the equilibrium position, we can apply Newton's first law of motion. For this, we're going to define our coordinate, downward direction for the x coordinate as our positive direction. With this coordinate definition, we're ready to apply Newton's first law of motion. Summation of forces in x direction must be balanced. So then let's apply our free body diagram here. According to our coordinate definition, downward is positive, starting from the active force mg, therefore same direction as we set in the free body diagram, positive mg. Then reaction force from the spring, so upward, opposite direction as we set, therefore minus how much? K over EQ times delta of ST, they must be 0. Therefore, from this we can come up with mg can be expressed as K over EQ times delta of ST. That's why we can have one expression from the consideration of equilibrium state. Then let's move to our free body diagram and kinetic diagram when our mass is in motion with a small deflection. So free body diagram, therefore FBD on the bar. We do already have outlined the body of the mass. On the outlined body, we're going to show all the forces acting on it, starting from the active force. From the mass, weight is applied downward direction. Why? Because gravity direction. How much? mg much weight of the mass applied. Reaction force from the spring. From the motion, we're assuming, let's clarify our motion at that point. This free body diagram, given very concise kinetic diagram, our inertial system, mass times acceleration in this direction, downward direction. Matching with this kinetic diagram, our mass at that point is moving downward direction. Therefore, spring-wise, it's stretched more downward direction. Spring wants to restore the energy. How much? Delta ST from the equilibrium already deformed downward direction, but with this motion, x much deformed downward direction, x much. Then spring force can be expressed multiplied by spring constant K over EQ for the spring force. That's going to be our free body diagram and kinetic diagram with motion. Once we have a free body diagram, then we can apply Newton's second law of motion. So summation of all the forces in x direction must be equal to B mass times acceleration in x direction. Using this coordinate definition, let's use this free body diagram for this left-hand side term. So therefore, mg downward positive, same direction as we set in the coordinate definition. And then let's move to the spring force upward, therefore opposite direction as we set in the coordinate definition, minus K over EQ times deflection delta of ST plus X. This must be mx double dot downward, therefore same direction as we set. From the equilibrium consideration, we have that expression. mg can be expressed as K over EQ delta of ST. Then mg, K over EQ and delta of ST can be cancelled off from this equation. So therefore, our equation motion can be come up with, let's start from the highest order, mx double dot. This K over EQ x can be moved to the other side, therefore plus K over EQ times x. This must be 0. Makes sense because we are under free vibration. Therefore, it is a homogeneous equation. And then this will be our equation of motion. Once we have this equation of motion, we also do know how to find the natural frequency. We can use this mass and the spring stiffness to find the natural frequency. Omega n can be found by square root spring stiffness K of EQ over M. So let's write down our final solution in this answer box. The equivalent spring constant can be expressed as like this. And the free body diagram, we already provided two different free body diagrams for equilibrium and for motion. And also our equilibrium motion was expressed as mx double dot plus k over eqx, free vibration, therefore zero, homogeneous. Once we have equilibrium motion, natural frequency can be found by square root k over eq divided by n. And then don't forget the unit, radian per second. That's going to be our answer. Thank you everyone. See you next time.